Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed how we will get the CRR value, CRR for magnitude 7.5 by using SPT data. Now, today I will first discuss that how we will get the CRR value by using CPT data. Okay, so that means I will continue the evaluation of liquefaction resistance of soil, and now we are discussing about the field test, use of field test data. Now that CPT, so that means you know the CPT, we will get the tip resistance or cone resistance and the friction resistance, so that is called slip friction. So again you go to my CPT lecture, then you will get that how the CPT this test is being conducted, and then how we will get the QT or the tip resistance or QC or the tip resistance, and how we will get the friction resistance or slip friction, how we will get. So, you will get all the information from there. So, now that if you have that tip resistance, so suppose we have the raw tip resistance that we are getting from the field, and that we have to apply correction. So, what are those corrections? So, if it is clean sand, again clean sand means fines is less than equal to 5%. So, if it is clean sand, then cone penetration resistance can be normalized with 1 atmosphere. Again, that is why it is called CQ. C is the cone resistance, 1N, that means the normalized by 1 atmospheric pressure. So, that is why it is called QC1N. 1 means the 1 atmospheric pressure, that is 1 ton per feet square or 100 kPa, and N means it is been normalized. So, that means that is why it is called QC1N. Okay. So, this is QC is the raw data, your tip resistance or cone resistance, and 1N means it is normalized by 1 atmospheric pressure or 1 ton per feet square or 100 kPa. So, that means it will be normal. How it will normalize? So, that means this normalized value I will get, this is QC. QC is the raw data, that is normalized by PA. You know, PA is the 1 ton by feet square or 100 kPa, and into CQ. How we will get the CQ? CQ is PA divided by sigma V dash or effective overburden pressure, and N you can see varies from 0.1 to 0.5 to 1 depending on the type of soil, and again CQ is less than 1.7. CQ cannot be greater than 1.7. Clear? So, QC is the field cone penetration resistance, PA is equal to 100 kPa, N varies from 0.5 to 1 depending upon soil type, and CQ is less than 1.7. Now, N is equal to 0.5 is appropriate for clean sand, okay, and in between 0.5 to 1 is appropriate for silt and sandy silt, and 1 is appropriate for clay. Clear? So, later on I will show you how I get the N value, proper N value, or how I will use this N value to get that CRR. So, it is clear. So, N value is for 3 different soil, the appropriate range, or for clay and clean sand appropriate exact value is given, but for silt or sandy silt the range is given 0.5 in between 0.5 to 1. Okay, so now from if you have the, now from here for the raw data I will convert it to again clean sand. Now that Q, that's QC1N, I don't know whether it is a clean sand or not. So I will get a raw data or the field CPT data, cone penetration resistance data, then I will normalize it. But I don't know it is a clean sand or there is a fine, or it is a sealed, soil is sealed or clay. So first, for that purpose, first I have to identify which type of soil it is. Is it a clean sand, or it is a clay, or it is a silt or silty sand? So first that I have to identify. So how I will identify that? So that identification we will get from this IC. What is IC? IC is called your soil behavior type index. Okay, soil behavior type index. So that is IC. So IC I will get from these equation, where Q I will get from these equation. Okay, I am not telling those equation because you can see those equations, and the terms are already been discussed, all the terms. And this is your F. F is what? Fs. What is Fs? Fs is the sleeve resistance or the friction resistance of the cone. And how you will get that? You will get the total resistance, you will get the cone resistance, you subtract it, you will get the slip resistance, or FC. Because those things have been already discussed in my CPT lecture. So that means here, now the question is, what would be the N value? Because initially when I start, I don't have any idea which type of soil it is. So because I have given for sand it is 0.5 N value, for clay it is 1, for silt to silty sand it is in between 0.5 to 1, but initially I don't have any idea what is the N value, what is the type of soil. So how I will decide what N value I will consider, because N value is required to get the IC. So I will discuss how we will get the N value, but now when I will get the IC, proper IC, then I will convert it to clean sand. Suppose there is sand, fines is there. So now similar to SPT, that QC normalized cone resistance, if there is fines is there, that will be converted to clean sand normalized cone resistance. Okay, so that will be done by this equation, that is Kc into this term. Okay, now what is Kc? If IC is less than equal to 1.64, the Kc will be 1. If IC equal to greater than 1.64, Kc can be determined by using this expression, this empirical expression. Now from how this expression is coming? This expression is coming from here. You can see that if it is, if you see this chart, the IC versus Kc chart, now if IC value is 1.6, you can see Kc is 1, this chart, that is the thing. And if IC value is 1.6 around or less than 2, the soil is sand or gravelly sand, it is not a mixture. So that's why Kc is equal to 1. So that means it is a clean sand condition. If IC is less than 1.64, then it is a clean sand condition, no mixture. So that's why the normalized cone resistance that I am getting, that is itself the clean sand normalized cone resistance. Clear? Now if your IC value is greater than 1.64, then sand is mixed with fine. Now it is clean sand, not a clean sand condition. Or it can be silt, it can be clays. When it can be silt or clay? If it is greater than 2.6. If IC is greater than 2.6, you can see 2.6, it can be silt mixture or even clays. Okay. So, but as I mentioned, we are now talking about the liquefaction resistance of sand. So that means how we will take care of that I will discuss. So right now you calculate the IC, and if the IC is less than equal to 1.64, Kc is 1, that means a clean sand. If IC is greater than 1.64, then you calculate the Kc, and that Kc you multiply with the normalized QC value or QC1N, and then you will get the QC1N clean sand. Okay, you can see that if it is greater than 2.6, it is silt or sand. and if it is less than 1.64 clean sand, in between 1.64 to 2.6, the sand is mixed with fine. Clear? So now once I get the this QCIN for clean sand, then I can use this expression for if the QCIN clean sand is less than 50, and if it is in between 50 to 160, then I can use this equation. So these two equations I can use, or if you convert it to clean sand tip resistance, then you can use this chart also. You can see this chart also, you can, or this graph or line you can use to determine CRR. Again, it is CRR or CSR as I mentioned, but now it is termed as CRR. But as it is previously called CSR 7.5, then both the terminology are being used here. So now it is, you can see it is valid for if it is less than 160, this normalized tip resistance, clean sand, under clean sand condition. So, I mean after conversion. Okay. So, if it is 60, less than 60, this equation is valid, and it is, you can see for less than 50 and in between 50 to 160, two equations are given. So, that you will get, and you will get the CRR 7.5. Now, the question is that how I will, the question is what N value I will consider when I calculate the Q, still it is unknown. Because if I know the soil type, then I can choose the what will be the value of N, 0.5 or 1 or in between 0.5 to 1. But I don't know the soil type. So first I have to know which soil type it is. Okay. Then I can apply these things. So first I have to calculate the IC, and to calculate the IC I should know the N. So to know the N value, the steps are that the first step is that you take N equal to 1. So that means I am assuming that soil is clay. Okay, first I am taking N equal to 1, because for clay N equal to 1, and calculate the Q. If N equal to 1, then this PA will cancel, it will be simply QC minus sigma V0 dash. Okay, so this can be your actually this will be a dash. So first you get the Q value. If the calculated IC is greater than 2.6, if the calculated IC is greater than 2.6, then our assumption is correct, because we assume N equal to 1, and you can see if IC is greater than 6, 2.6, it can be clay, 2.6 or silt mixture or clay. So that means if it is greater than 2.6, then soil is classified as clay soil and the analysis is completed. And the soil is too rich to liquefy. However, sample should be tested to confirm the type of soil and the liquefaction resistance. So that means we have to test that soil, and we have to identify that the liquefaction, and we have to confirm that the liquefaction will not occur. Okay, so that's why we can use those field tests, laboratory tests, and we have to confirm that liquefaction will not occur. The sample should be tested to confirm the type of soil and the liquefaction resistance. Okay, or there is a criteria called Chinese criteria may be applied to confirm that soil is non-liquefiable. So right now we will use the Chinese criteria as it is recommended in these methods. So what is Chinese criteria? So Chinese criteria, it is said that liquefaction can only occur if all the following conditions are satisfied. All the following conditions. What are those conditions? That the fraction finer than 0.005 millimeter is less than 15%. So that means if the amount of fines, what is fines? 0.005 millimeter finer. If that fines amount is less than 15%, then the liquefaction will occur. If it is greater than that, then the liquefaction will not occur. The possibility of liquefaction is nil. Okay. or liquid limit is less than 35%, or natural water content is greater than 90% of liquid limit, and the liquidity index is 0.75. Okay. So that means you have this Chinese criteria say if all these 4 criteria are being satisfied conditions, then the liquefaction will occur. If any of them will not satisfy, the liquefaction will not occur. If these all the conditions are satisfied, then the liquefaction will occur. So if you find that my IC value is greater than 2.6, then it is clay. Then you test it and confirm it is clay, and then also test it and confirm the liquefaction will not occur, or you can use the Chinese criteria to confirm that the liquefaction will not occur. Clear? So that is, if it is clay, it is that means limit we are assuming is too rich to liquefy. This soil is too rich. Soil is too rich with clay. Okay, to liquefy. So that means next is that if the calculated IC with n equal to 1 is less than 2.6, then the soil may be granular in nature, and recalculate Q and CQ using n equal to 0.5. Okay, if your n is equal to, if you take the n equal to 1 and still you will get the IC is less than 2.6, then the soil may be granular in nature. Now you recalculate it, consider n equal to 0.5, because for granular soil n equal to 0.5. Now if you recalculate, if the recalculated IC with n equal to 0.5 is less than 2.6, then the soil is classified as non-plastic and granular, and use the recalculated IC with n equal to 0.5 to determine the liquefaction resistance. Okay, so that means first you will consider n equal to 1, and if the IC value is greater than 2.6, then it is clay. If then you confirm that the liquefaction will not occur, or will, okay, and then if it is IC is less than 2.6, then it is granular, soil may be granular in nature. Now you recalculate the IC, considering n equal to 0.5. Now after recalculation, if the IC value is again less than 2.6, then it is confirmed the soil is granular in nature and non-plastic, and then you use that n value to calculate your IC, and from there this QC clean sand, and then CRR value. Clear? Now if that is the third condition. Now when you consider n equal to 0.5 and you get IC equal to less than 2.6, then it is granular. But if you consider n equal to 0.5 but still you get IC greater than 2.6, then the third condition, that if the recalculated IC with n equal to 0.5 is greater than 2.6, the soil is likely to be very silty and plastic. Then what you have to do? Then you recalculate the IC using n equal to 0.7, because in case of silt or silty sand or sandy silt, the range of n is 0.5 to 1. So you take the average value, that is take n equal to 0.7. This recommended intermediate IC, then what IC you will get, that should be used for liquefaction calculation in case of silt or sandy silt. Okay, and the sample should also be tested to confirm the type of soil and the liquefaction resistance that I am getting from this calculation, or Chinese criteria may be applied to confirm whether soil will be liquefied or not. Clear? These are the steps to get the n value or to identify the type of soil, and then with that n value we will get the IC, with IC we will get the KC, with KC we will convert it to clean sand tip resistance, and first you have to normalize that, normalize clean sand resistance, and that normalized clean sand resistance we have to use to determine the CRR by using this CPT data. Clear? Okay. So now I will go to the third method, that is by Vs, velocity of shear wave. Now this is the chart for this. So these actually from these equations or these charts are developed or these lines are developed. So this is or vice versa. Actually from this equation this is developed. So this is for less than 5% fines, this is 20% fine, this is 35% fine. Okay. Now this is the equation where you will find this Vs1, this is Vs1 is the corrected shear wave velocity. This again 1 means again it is normalized by 1 atmospheric pressure. You can see Vs1 is equal to Vs, Vs is my raw data, velocity of the soil, it is normalized by Pa divided sigma V dash into 0.25. Okay. So Pa is equal to 100 kPa or 1 ton per feet square. Okay. So sigma V0 is the initial effective vertical stress or overall pressure. A unit of sigma V dash and Pa should be same. Okay. Now Vs1 dash is the limiting upper value of Vs1 for liquefaction to occur, and A and B are the curve fitting parameters. Note that the curves are drawn, these curves are drawn with a final value of A and B is equal to 0.022 and 2.8 respectively, and Vs1 dash values are varied linearly for 200 meter per second for fine contents of 35% to 215 meter per second for fine contents of 5% and less. So that means these when these curves are drawn for 35% fines, then it is taken as Vs1 dash is taken as 200 meter per second. If it is 5% and less, then it is taken 215 meter per second, and in between that it is linearly varying. Clear? And A and B values are taken as 0.022 and 2.8 respectively to draw this curve. So when I use this equation, I will also use this A and B, these two values, and Vs for different fines, these two values, and if it is in between that, we linearly vary that Vs1 dash. And Vs1 I will get from the raw Vs data, and then I will get the CARR 7.5. Clear? Or you can use this chart also, because as I mentioned, these charts are developed by using these values. So I will use these values and you will use this equation. Next, as I mentioned that we are always talking about that now we will get the factor of safety, and we are always talking about CRR 7.5. So that means all these values or these charts or equations are valid for magnitude or moment magnitude 7.5. Okay. Now if the moment magnitude has the different value, maybe more than 7.5, maybe less than 7.5, then we have to apply a correction factor. So that is called magnitude MSF. Okay. So that is called your magnitude correction or scaling factor. So that is called MSF. So in addition to that, there are two other corrections should be applied. What are those two corrections? One is K sigma, another is K alpha. What is K sigma? And before that, this is the factor of safety. You know, factor of safety is CRR 7.5. That is the stress required to cause liquefaction or the resistance stress divided by stress developed during an earthquake. So that is your factor of safety. And if it is your magnitude, moment magnitude is 7.5, then no magnitude scaling factor or correction factor is required. That will be 1. But two other correction factors are required for two special cases. So what are those cases? Okay. So those cases, first one is the K sigma, the correction factor K sigma, which is the shear stress required to cause liquefaction increases at higher effective confining pressure which is greater than the field performance data bed. Sometimes during the test, these equations that we are developed, so for that sometimes we can see that for higher confining pressure, that your liquefaction, the stress required to cause liquefaction, that increases, but that confining pressure actually higher than the or greater than the field performance database. So that's why for higher confining pressure, the value that we are getting, actually we are getting higher factor of safety, because the stress required to cause liquefaction value increases. Actually for higher confining pressure, the value that I am getting by using all this calculation, that is I am getting a higher value. Actually in the field it is a lower value compared to the value that I am getting. So that means for higher confining pressure or for higher effective confining pressure or effective overburden pressure, what is that value? If it is greater than 100 kPa, then these things will come into picture. Suppose if your effective overburden pressure is, or sigma effective stress, vertical stress, sigma V0 dash, if effective overburden pressure is greater than 100 kPa, then the stress required to cause liquefaction that I am calculating is actually the greater or the higher than the field condition. Okay. So for this high confining pressure, we have to reduce the factor of safety. Clear? Because I am getting the higher value which actually exists in the field. So I have to apply factor of safety. So that factor of safety, or apply the corrections. So that correction is K sigma. So how these are the different chart. So this is my effective stress, unit is ton per square feet, and this is K sigma, and or I can use these equation also. Okay, the sigma V0 dash divided by PO F minus 1. What is F? Because this F is function of relative density. So if the relative density in between 40 to 60, F is 0.728, and if relative density between 60 to 80, F is 0.6 to 0.7. Okay, so you can see it is F is 0.8 for 40, F is 0.7 for 60. Okay, F is 0.6 if it is greater than 60. That means 60 to 80 we can get 0.6 to 7. So for 60, in between 60 is 0.6 to 7. So I can get in between 0.7 to 8 if it is in between 40% to 60%. If it is greater than 60, I will go for 0.6 to 0.7. Okay. So for that means that simple word, for 40% relative density, I will take F equal to 0.8, 40% relative density, and for 60% relative density, I will take F equal to 0.7. Again for 60% relative density, I will take F equal to 0.7, and for 80% relative density, I will take F equal to 0.6. So this is the range that, and your K sigma is correction factor for effective overburden pressure greater than 100 kPa, and F is an exponent which is a function of site condition such as relative density of the soil, stress history, over consolidation ratio, etc. Clear? So this way I will get the K sigma. Clear? So this is my chart also. So from this chart also you will get the value, or by using this equation also you will get the value of K sigma. This is for relative density 60, this is for 60 with different F, it is greater than 60, and this is less than equal to 40. So this is less than equal to 40. So either you use this chart or use this table equation. Now another is the K alpha. What is the K alpha correction factor? Suppose if your site is a sloping ground, okay, so what will happen? There will be a slope, and there will be already a shear stress will exist along the failure surface of the slope. Okay, so I mean there is already a shear stress, static shear stress is there in the soil before applying the shaking. So that existence of the static shear stress, or that if you have a site which is supported by heavy structure or supported by a building, where due to that building already a static shear stress is existing in the soil. Clear? That means suppose if you have a soil, there is no structure, it is a flat land. So that means here, as I have shown that the shear stress before applying the shaking, this particular plane is not existing in shear stress. But when we apply the shaking, then the shear stress will develop. But in field in such a condition, if there is sloping ground, already there is a static shear stress. So in the shaking, the shear stress that will develop, there is just shear stress due to cyclic loading, cyclic shear stress. But before the shaking is applied, if there is a shear stress already developed, static shear stress already exists in that soil, or if there is a foundation or the buildings, because of that already shear stress is developed, static shear stress, then that will also create effect and it will reduce the factor of safety. So that you have to apply correction factor, but that depends on the soil types, whether it will reduce or increase. Okay, because here you can see that this is the correction factor for initial or static shear stress, or this is alpha, can be, there is a term alpha which you will get that static shear stress divided by sigma v dash. Sigma v is the effective overburden pressure. So that is the static shear stress. Note that liquefaction resistance of dilative soil, moderately dense to dense granular soil under low confining pressure increases as static shear stress increases. So that means if it is a dense to dense, moderately dense to dense granular soil under low confining pressure, then the factor of safety will increase because of presence of static shear stress that increase the liquefaction resistance for dilative soil. But if it is a loose soil, loose to moderately dense granular soil under high confining pressure, which is the case we are more worried or concerned, then it actually the liquefaction resistance decreases as the presence of static shear stress or static shear stress increases. So that's why it is very important to consider if it is soil is loose, where your factor of safety will reduce, because presence of this static shear stress, it will reduces the factor of safety, because the your cyclic resistance will reduce or decreases as static shear stress increases. So how I will get this K alpha? So these are the charts are given. So this is first one is the proposed by Seed and Harder 1990, where this is it is given in terms of relative density. This is K alpha, this is alpha. Alpha I will get from here. I will discuss how I will get the static shear stress below foundation. Slope you can know how you will get the shear stress, that from the slope stability analysis you will get that. Okay, so that means here this is K alpha, this is for relative density 30%, this line is for 45 to 50, this is for say 55 to 70. So in between that you have to consider, and if you say it is 40%, so 40% line will be around here. Okay, and from there you will get the K alpha if you know the alpha value. If you know the relative density, if you know the alpha, you will get the K alpha. But the Idris and Bollinger 2003, they have proposed also these two charts for sandy soil in terms of N160, and remember that this Idris and Harder chart is valid if your sigma V0 dash is less than equal to 3 ton per feet square or 300 kPa. Similarly, the Idris and Bollinger has proposed two charts. One is for if this is sigma V dash divided by Pa is equal to 1. That means if your sigma V dash is 100 kPa another is if your sigma V dash is 400 kPa. In between that you can linearly interpolate. So this is if you know the alpha and if you know the N160 value of a soil, then you will get the K alpha value. And you can see that if its N160 is around 10, then your K alpha is 1. If it is N160 is less than 10, that means a loose sand or moderately loose sand, then you will find that the K alpha value is less than 1, that means factor of safety will reduce. But if it is greater than 10, that means a moderately dense to dense soil, then the factor of safety will increase. So if it is increases, this is not an issue, but it will not reduce your factor of safety, but again definitely you should consider that. But if it is loose sand, then it will reduce the factor of safety. So that is the most critical part. That's why you have to consider the presence of static shear stress in the soil when it's static before applying the shaking. So that means first you calculate the static shear stress, then you determine the alpha, and if you know the N160, then you will get the K parameter, your K alpha. And even if you know the alpha and the relative density, then also you will get the parameter K alpha or correction factor K alpha. And it is more critical for loose sand. You can say your factor of safety will decrease because K alpha value is less than 1. For dense sand it is greater than 1. Okay. So that's why these two, basically three corrections. One is the your magnitude scaling factor or correction factor. One is the for effective overburden pressure. If you have very high effective overburden pressure, then you which is greater than 100 kPa, you have to apply the correction factor. And another is the presence of static shear stress. You have to apply the correction factor. Okay. So these are the all. Okay. So I am finishing my lecture, today's lecture here. So now I have discussed about the two correction factor. One is K alpha and K sigma. One is due to the high effective overburden pressure. Another is due to the presence of static shear stress. Now still one correction factor is MSF, magnitude scaling factor or correction factor is remaining, and that I will discuss in the next class. Thank you.